So this is the AP Calculus BC content review session. Today we'll talk about Unit 1, limits and continuity, and then we'll have a short 5-minute break, and we'll come back with BC integration techniques part 1, and that will be continued in a later session we'll talk about at the end. Ms. Kimberly Hill, Kim Hill, will be presenting. She teaches at Madison Central High School. I'll let her introduce herself in just a second. You can find your handouts at the bit.ly given right there. Just a disclaimer I need to read. While this online review session is intended for Kentucky audiences, space permitting, we welcome students from other areas. We will do all we can to provide every student with an equitable opportunity to learn. During the session, we encourage participation, but please know that any participant causing a disruption to the session will be removed. The cameras are off and the mute is off. So again, I'll be monitoring the chat, so let's keep it school appropriate in the chat. You can follow Advanced Kentucky on Facebook and Twitter. If you need to contact me, there's my contact information. I am the Access to Algebra Content Manager, but before joining Advanced Kentucky, I taught AP Calculus AB and BC for many years. I'm also an AP Calculus exam reader, and last year I was a table leader. The microphones will be off, video will be off, but chat's on, and I'll monitor that. After today, you can find the recording here at the bit.ly/ADVKY. So I'm going to stop sharing my screen, and I'm going to let Ms. Hill take it from here.
All right.
All yours, Ms. Hill.
Thank you so much. Okay, good morning. As he said, I'm Ms. Hill, and I have been teaching for 25 years. I've been doing the AP BC content for 7 or 8. I lose count on that part. The 25 is important because it's getting me to retirement. So I've been teaching 25. I've been doing AP Calculus BC for quite a while now, and went to all things Advanced Kentucky my first few years, and it was amazing. And that's how I trained myself. So for those of you who are teachers, I saw there's a couple of first-year teachers on there. My advice to you is there are tons of amazing teachers out there with wonderful videos. So put yourself at night on your computer, watch other teachers teach subjects and content, and that's how I learned. This is how it's in the textbook. This is how it's on the exam. So my advice to you for first-year teachers is to do that. So what we're going to look at today is limits, continuity. We're going to just hit a little bit of differentiability, and then move into the integration techniques. So Michael, is there anything else you need to do, or I'm ready to roll?
You're ready to roll.
Okay, so if you've got questions at all, please put it in the chat. Michael's going to be watching that, and he will answer all questions he can in there. Anything he wants to bring up to address to the whole group, we will do that as well. Don't be shy. Make sure if I'm rolling through and you need me to wait for a minute so you can catch up, or if you've got a specific question about what I'm talking about, this is for you. So it's not about the Kim Hill show. This is for you to get as much as you can out of today. So we're just going to jump right in and not waste any more time with anything else. So this is the first study session. I would encourage you to come to all of the Saturday sessions. There are some amazing people that's going to be presenting. So if you leave today thinking, well, she wasn't all that great, the ones coming behind me are wonderful. So make sure you keep coming back. So limits, and this first topic is more of an AB topic, what I would consider AB. But as you know, if you've studied the exam, AB is a big portion of the BC exam. So you can't just leave it behind and forget it once you've covered it. So limits is a big deal. It's kind of our base, what we build everything from the beginning. So since most of you, you're doing AB and BC all in one year, you probably have done limits recently. My students haven't done limits like this since last year when they had Miss Gray. So we have to go back and really review this. So that's what I'm going to do. We're going to go back and review a little bit. The session today is more about how does it look on the exam. So we're going to look at a lot of questions, multiple choice questions, and how it would look on the exam. But before we do that, let's get a little background. So we want to look at not only what is a limit, but if we're asked to show or justify that a limit exists, what would we have to say on the AP exam? Because we all know that justification piece, that's a point sometimes. Anytime you see show, justify, you don't want to ever lose that point because, or you don't want your students to lose that point because you didn't know what to tell them. So if we want to show that a limit exists, these are the three things you have to state. And so you want to make sure as a student that you make sure you state that the limit, and remember the little negative means from the left, that it exists. You have to show that the limit from the right exists. So we have to know that both sides exist, and then more specifically, they have to be the same. So you would have to have all three in your justification to say that that limit does exist. And so a lot of times this is when you're going to use this when you have a graph. If you have a piecewise function, and we're going to look at a couple of those today. If you can't read my writing, please just tell me and I'll try to write nicer. I try to write fast, and when I do, I talk fast and I write fast, and sometimes it doesn't work out. So make sure you let me know. So just real quick, if we are thinking about a graph and we're trying to decide, does a limit exist from a graph? So just, I wanted to give you at least one little piece here on the front just so you could see it. So let's say our graph looks like this. And it doesn't have to be perfect. It doesn't have to be anything special. And I should have put, let's see. Let's make a vertical asymptote over here. Just all kinds of things could happen. On this side, let's go ahead and extend it. Let's make this a point. Okay, sorry that as I'm thinking, I'm adding stuff to what I want to put on my graph. Okay, so let's just think about what's going on. And I'm going to tell you kind of like how I tell my students to do. So when we're first learning a concept, a lot of times, and like I was telling Michael earlier, my daughter hates this stuff, but I try to put it in a way that helps you remember it. And if you remember the silliness, then maybe that'll trigger your brain back to the official calculus part. So what I tell my students, if we're looking for a limit, so let's say that this limit right here is at -2. So I'm trying to do the limit as x approaches -2, and we'll call this function f of x. Okay, I don't care about other parts of my graph. So my students tend to get all torn up about what's going on way out here. Well, I don't care. What I'm caring about is x equals -2. So I have them draw a line through -2 and just say, okay, that's what we're caring about. So I'm caring what's happening from the left of my wall and from the right. And then I tell students, go to the left piece. So here's the piece I'm talking about from the left. So if I don't have any part of the rest of this graph, and all I care about is what's happening on that side. So I always tell my students, it's like you're driving a car. So if I'm driving a car on this side, where is my car trying to get to? So if I'm driving my car on just that left side, we'll say that's at 3. It's trying to get to 3. So as I do my limit from the left, I know my left car is trying to get to 3. Now, if you notice, there's a hole there, but it's okay. And what I tell my students is, it's like you're in a car and you're driving to get to a party, and this is your house. So if this is your house, you got there and nobody was home. I don't care that nobody was home when I got to the party. What I cared about was where did I get to? So this car got to 3. When he got there, he was in the wrong place. That's not where the party was happening. So, but he still got there. So then I look from the right. So again, cover up the part of your graph you're not caring about. So I'm caring only about the part of this graph that's coming in from the right. So there's lots of stuff happening over here to the right, but I really care what's really close to my line I drew. So I'm going to just start somewhere close and say, okay, here's my car, and I'm driving towards that line I made. Because I notice with students, when we first start learning limits, they're not sure because they're used to reading a graph left to right. So they want this to start here and go this direction. So from the right, what's happening? Well, when you're talking about limits, we have to get out of that notion of reading your graph left to right. Instead, you've got your divider here, and I'm saying if I go on each side of my divider and I'm trying to come into it, what am I doing? So you're approaching this x value. So we're trying to say as x approaches -2. So it's approaching, meaning it's coming in from both sides. So now this car ended up down here. We'll say this is at -1. Okay, so we would have the limit as x approaches -2 from the right is -1. Now, if that limit is going to exist, my 2 cars had to end up at the same place. So if the limit exists, so I'm showing the limit exists from the left. I'm showing the limit did exist from the right. So I have accomplished number 1 and number 2. But that's not good enough. I have a limit from the left, I have a limit from the right, but are they the same? And so then I have to go back and decide, did my cars end up at the same party? Nope. This one was at 3. This one ended up at -1. They are not equal, so the limit does not exist. So that limit will not exist because they did not end up at the same place. Now, another thing that you may want that your students or that you as a student may be asked is, what is the actual value? So then if it asks me, well, what is f of -2? That's saying, well, where does this function have value? Where is there actually a point? So it's meaning on this line, where on that line do you actually have a value? That house is empty. This car was lucky. It got to the right place. So when it got to the house on your line, there was a party going on inside. So this car had the correct address. So my actual value would be at -1. So all 3 of those things would have to equal if you were going to have a limit that exists. Okay, so just real quick, if we look at the limit, I'm sorry, I'm writing down my page like this so you guys can add to yours. So let's say we wanted to know, does the limit as x approaches -1 exist? So does that limit exist? So in my mind, I'm thinking, okay, there's 3 things to show. I have to show the limit as x approaches -1 from the left. I have to show it exists. And not only do I have to show that it exists, I have to show that it is equal to this limit. And I said something wrong. I have misspoken. So let's go back for just a second. So we have to show that the limits exist. And I think I said this. And if I did, I apologize. We don't have to show that it's equal to the function value. And I think I said that. So all you're having to show is this statement right here. So you have to show that they equal. The function value would make it continuous. And we're going to talk about that in just a minute. So let's look at this one. So again, I tell my students, we're talking about just -1 right here. So if I'm at -1, I want to know as I'm approaching from the left and from the right, are they the same? So I'm going to put my little car on here on the left and see where he's going. I'm going towards that blue line, and it appears that it's going to 3. So on the left, I went to 3. Now if I come to the right side, here's my little car. Where is it driving to? It's driving towards my blue line. If I'm driving all along, it also reached a height of 3. Now here's another thing you want to make sure you understand is when you're giving your answers for a limit, make sure you understand that you are giving a y value. So it is very, very important. I'm going to tell you what x is. We're taking the limit as x approaches -2. You're going to tell me back what height am I reaching. So if my x's are coming in, what height am I coming into? Is this x coming in at this height and this x coming in at this height, so my limit does not exist? Or are they coming in at the same height? And if they are, the limit does exist. So on this one, the one from the right was also 3. If you can say both of those things are the same, we do have a limit. So the limit as x approaches -1, not specifying left or right, is 3. Now, if you had to justify this on an AP exam, you would want to say that the limit from the left is equal to the limit from the right. And this is one way that I've seen it written. You would say the limit from the left is equal to the limit from the right, and it's equal to 3. Therefore, the limit as x approaches -1 is 3.
Kim, I had a question. I answered it, but I'll say it to everyone. They asked about,
Okay.
Is it okay to write it in words or notation? And again, as my experience as a reader, it's the important part is that you do, usually this is the continuity question you're getting there,
Right.
that you've talked about the left and right-handed limit. If you say it in words correctly, then we would have to give you that point. Many times students do not explain things correctly in words. They leave something out. So your best bet is to be familiar with the limit notation. That's gonna, the reader is gonna see that immediately and know that you did what was asked. Yes, they're gonna read what you say, but you have to say it correctly. So yes, both would get credit, but I would strongly recommend doing the limit notation.
Is there a better way than this to show it, or is this pretty much standard? That's what they're looking for.
That's standard.
Okay.
Yes.
Good questions. Keep them coming. Keep them coming. Okay. So that's telling me that the limit exists. So the things you should be able to do, so that's just a little background, a little, don't forget this is what it means. So that's from a graph. So what we're going to talk about for just a few minutes is how do we determine limits from a graph? We've just talked about that. How do we compute limits algebraically, and limits and asymptotes and how that all works. So if you look in your packet, let's look over at number, let me see which one I want to do first. Let's look at, just real quickly, let's look at number 5. So let's look at how we might see this on just a multiple choice question. And like Michael said, most of the time it's going to be asked more about continuity, and we're going to talk about that, but I just wanted to double check. So what I want you to do is I want you to look at number 5, and I'm not going to give you much time. So if you don't have time to process before I give you an answer, that's okay. We just don't have a lot of time today. But I want you to read number 5, because the AB and the BC test both love these Roman number 1, 2, and 3 questions and make you pick which one's true. So I want you to try this one. And if you don't care to put your answer in the chat box, just so we can kind of see where everybody is, that would be wonderful. If you're shy and you don't want to, that's okay too. So read it and see what you think. Okay, I see a lot of C's. So if we look from the left, so look at our choices. We're just trying to show, as x approaches 2 from the left, does that exist? So if I look from the left, it does exist. My car is approaching whatever number this is. I don't know what it is. Let's say it looks like it could be about 2. Okay, so that looks like it's approaching 2. It does exist. Then I look from the right. It looks like it's probably approaching 1. I don't know for sure, but in general, it looks like it's going to 1. So from the right, it does exist. So then I have to decide, does the limit as a whole exist? And the only way for this to exist is if these two are equal. So this one looked like it might have been around 2, around 1. They are not equal. If they're not equal, this one cannot exist. And so it's going to be 1 and 2 only. Very good. Okay, go ahead and look at number 17, and then we're going to move on. So look at number 17. Same thing. Tell me what you think in the chat. So there's number 17. When you think you know the answer, put it in the chat again. Good deal. Okay, so we look at our, and a lot of times I tell students, if you're not sure what to do just on the AP exam, look at the answer choices, and sometimes that will trigger you as to what they're wanting you to do. So I know I'm going to either have to do 1, 2, or 3, 1 and 2, 1 and 3. Okay, so I'm going to look at 1. And as I look from the left and the right, I'm not going to draw my car this time. This one's going, it looks like, to the height of 1, 2, 3. So again, you're looking for a height. You're looking for a y value. Don't forget that. Put that in your brain. Your answer is the height, the y value. So this one's approaching 3. If I drive in from this side, I'm also approaching 3. So that limit does exist. So 1 does work. So it can't be 2 only. It can't be 3 only. And when I even to this day do a practice test, as soon as I know something is true, I'll go down to the choices and start eliminating so that I can see what's going on. So now I need to decide about these two. So here's this one. Again, if we drive in from this side, drive in from this side, they're both approaching probably 4. So that one does exist. So then it can't be this one. It can't be this one. I wouldn't even have to check the last one. My testing brain would tell me, I'll still check it just in case you've messed up, but that would be a time saver on the test if you didn't have to check the last one. So this one, if we look at x equals 4, this car drove into about 4 from the left. From the right, we're at a height of about 1. So it does not exist. And those, since they don't equal, does not exist. Okay, I do think I want to look at number 19. And Michael, pay close attention to this one and make sure I do my notation right on this one. I meant to ask you about this before. I know how I think about it, but I want you to chime in if you think differently. Number 19 is a composition. So the AP exam doesn't like to leave anything just normal. So this one always trips me up every time. And so I want you to think about this because it's a composition. And if there's a better way for me to write this, and or any of the teachers that's on here today, if you've got a better way to think about this, please share. Sorry. If you're not sure, I've put a hint up there. And I'm eliminating a most common answer choice mistake. Okay, just for sake of time, because it's already 10:30, I'm going to talk about this a little bit. When you have a composition, the way I've seen it the most, the way I feel like it's done, and I don't know that this would be one that would ever be on a free response, just making sure you know how to do it for a multiple choice. You would do the inside portion first. So we would do the limit as x goes to 1 of g of x. So we would go to function g. The limit is 2. And then we would go to function f, and the function value is 3. Okay, so just real quick, I want to move on to look at the last parts of our notes. So let me go back.
Ms. Hill, are you going to do any more of these ones, or is that it?
I'm not going to do, I'm going to go down and do some of the 1, 3, 6, 7, and 18.
Okay, I was saying this is one of the ones that there's harder ones that people argue about. As for example, if that graph of f was discontinuous at 2, those are the ones that people really, because the notation doesn't work. You can't, it's not f of 2 if that function is not continuous. You have to look at the limit. You'd have to look at the limit as you approach 2 from the left, because you approach 2 from the left, from the bottom, from both sides on G. You know the ones I'm talking about?
Yes. Do you have one in particular you want to share?
I don't. I just thought about it. I just thought about that. That's those are really, really tricky, and they come up among teachers every year.
Yes, and Melanie and I talked about that too, about doing one, but since it wasn't in the NIMSY packet, I didn't add one in.
I don't have one either. I just want to watch out for that. I just want to mention that. I thought about it. Those are tricky.
So students, if I would advise you to do, as Michael said, and is look for ones that aren't continuous. So if this is a continuous graph, so no big deal. So ask your teacher to look for a question like this to where the function, the outer part, the F part is not continuous, or so that you know how to approach this in every aspect of it. So like I said, I just used the ones that was on the NIMSY packet, so I didn't pull one of those.
No, I did the same thing. Yeah, I did too. And that's why I think sometimes those shock teachers when they see them from the college board.
I'll try to find one. I'll make myself a note, find one that's not continuous, and I'll send it to Aaron and have him post it with our staff so that you'll see one. So
awesome.
Not continuous limit. Okay, I'll make sure I find one of those and get that to you all. Thank you, Michael. All right, so going back to the front. So one, we've looked at what do we do with graphs. So now another big deal is algebraically. So if we think about limits algebraically, let me scoot my paper over a little bit. Don't forget your first line of defense is always substitution. So I'm going to write some things down here for us, just some little notes. So if we are computing limits algebraically, you're going to sub in first every single time, and you're going to pray to the math gods that somehow you got a number and you don't have to do any more work. But sometimes there's work to do. So don't forget when you're doing limits that sometimes you have to do a little bit more. So you sub in if you get just a regular old number, something nice, doesn't even have to be a pretty number, just so it's an actual answer, you are done. Finished, you are happy, and you move on to the next question. But now with that, don't forget 0 over a number is 0, and you are still done. And that's when we start talking about, 0 in the denominator and all this, students tend to think that a 0 in the numerator is going to cause trouble too. It does not. It's just 0. So you're hoping for that. If you get 0 in your denominator, he's a bad guy. That's what I tell my kids. This is bad, and we have to think more about this situation. So 0 in the numerator, we don't care. But 0 in the denominator, we got to do a little bit more thinking. And if you remember, you learned something called indeterminate form. You can use L'Hopital. There's all kinds of things you can use to fix problems. So this means we could have a problem that can be fixed, or we could have a problem that can't be fixed. So if you get 0 in the denominator, you have two options. One, if it's a number over 0, your limit does not exist. So you can't do that. You can't do anything about a number over 0. It just doesn't exist. Move on with life. And again, I always say silly little tricks to my students to help them remember things. My daughter hates it. So you can either listen to this or you can take this or not. It's up to you. So I tell my students, use this little trick to remember or don't. I don't care. So when you see 0 over 0, when I see that, I see a little snowman. And I tell my students, if when you sub in, you get a snowman, you get 0 over 0, or if you're doing limits to infinity, you may get infinity over infinity. So I think of it as a little snowman, and I always say, and I know this is silly, but I would say, oh no, he's melting. We've got to fix him somehow. So we either have to take him to Le Hospital to be fixed so he doesn't melt, or we have to do some algebra to him. So this one is fixable. So this is where you have like those holes and things that we can remove, and a piecewise maybe, I don't know, all kinds of things you could have. So he's fixable. So how do we fix him? Remember, you always have L'Hopital, and we're going to do some examples of these. We could do L'Hopital. You could factor and cancel. You could do conjugates. That's like when you have something like the square root of x plus 3, its conjugate would be the square root of x minus 3, and you multiply by the conjugate. So you may want to make yourself a note, multiply by the conjugate. We have common denominators. I was trying to think of the other one. Any algebra that you have done in your life up to this point to rewrite functions is still legal. So all those things you're allowed to do. And then sometimes we can look at something, and especially if it's the infinity ones, a lot of times for those, we look at our horizontal asymptote rules to see what happens. So any of those things are possible. This one is the most popular. It's the one we use the most. So let's look at what does that look like as far as questions go. So let's look at question number, which one do I want to do first? Let's do number 12. So go to number 12. I'm sorry you're having to flip around in your packet so much, but so let's look at number 12. I always want to give you guys a second just to look at it first. So if I think about substituting, we can't really substitute infinity in, like that's technically not correct. But in our mind, we can think, ooh, if this was going, like, is this going to actually grow? So as I sub in numbers that are bigger and bigger and bigger and bigger. So as I sub in x equals 1, x equals 2, x equals 1,000,000, x equals 1,000,000,000, as that x is going to infinity, what's happening? Well, my numerator is growing. So as I put numbers in for x, this is growing. As I put numbers in for x, this is growing. Now, and again, if you are on a multiple choice question, it doesn't matter as much. But on free response, one of the things that some of the sessions I've learned is that they do not like to see that this is equal to like infinity over infinity, or if you get one that's equal to 0 over 0, they want to see those separated out. And so you would show.
You're correct, Ms. Hill. It's worse than dislike.
Okay.
You don't get the point. So don't say
so
equals 0 over 0.
So when we do these as a multiple choice, I'm going to go ahead and write them the correct way just so you get in that habit. Because here's the problem. We get lazy on multiple choice. And then when we get to a free response, we forget that we were being lazy. We think we were doing that all correct. So we're going to write this in the correct way. I would have to show on a free response. Now, again, if I were on a free response, I would have to do this. I can't just say it. So, and these are the little things I think these trainings are helpful for. So anything like that, yes, I can post a key. Anything like this that I have learned that I made mistakes on early on, I'd love to share with you all. So the limit as x goes to infinity of 2x minus 1 times 3 minus x is equal to infinity. And Michael, if there's a better way, chime in. And then you would also show for the denominator.
That's perfect. That's exactly what they want.
Okay. And that's also infinity. So you can't just do this. You have to make sure you make both of these statements, because you would hate to know the content, know what you're trying to say, but don't say it correctly and lose your point. So don't lose points for that kind of thing. So you're going to know that it's infinity over infinity, which means this one has a limit. Like we can do something with this. So this one's fixable. So it's not going to be non-existent, and we have to figure out what it is. Now, at this point, you can do all kinds of things. This is what I would advise my students to do. If I am going to infinity, so understanding the relationship between going to infinity and your horizontal asymptotes are really important. So if you think about a graph, And we're looking for the limit as x goes to infinity. So if I think about my graphs behaving however, all I care about is what's it doing way out here. And so when you think about what that means, and I know that's a horrific graph, I apologize, but, and I'll make a neater answer key that I'll post. So as I go way out here to infinity, what am I doing? Well, if you think about that, that's just your horizontal asymptote. So if you think about what your horizontal asymptote is doing, that's what your graph is doing at infinity. It doesn't tell us anything about what's going on inside the middles, but what's going on out there at those infinities. And so if I'm thinking about horizontal asymptote rules, then I'm just thinking about my highest degree. Because remember, your horizontal asymptote rules say if the degree of the numerator is higher than the degree of the denominator, then you don't have one because it's going to infinity. If the degree of the denominator is bigger than the numerator, then let's think about what that means. If my denominator in a fraction is growing the biggest, the fraction as a whole is shrinking. So if you think about if you had 1/2, 1/10, 1/100th, 1/1,000,000th, that fraction as a whole is going to 0. And then if they're equal, you use your leading coefficients. So I'm going to go back here, and to save time, I'm going to think, what would my degrees be? So if I had to FOIL this out, that would be 6x, 2x squared. So my 2x squared piece is the biggest. If it helps to FOIL the whole thing out, you can. So if I FOILed out my whole numerator, I would end up with 6x minus 2x squared minus 3x plus x. So the only one I really care about is that minus 2x squared because it's the highest degree. This one, I would have x squared plus 3x minus x minus 3. Again, you're looking for your degree. They're equal, so it would be the leading coefficients. So my leading coefficients would be -2/1. So that's what my limit to infinity would be.
All right, Miss Hill, can I told somebody to answer a question. I think
Yes.
we got a little confused. I confused them talking about the correct notation. So the question was, could they just do what you just did with the degree rules if it was a free response? And the answer is yes. You would not need to write anything else out. What we were talking about with the limit, we have to type the right top and the bottom, is if you approach this problem by using L'Hopital's rule. If you started taking derivatives of the top and bottom and therefore were using L'Hopital's rule to answer it, yes, you would have to have written this stuff out. If you did what Ms. Hill just did by looking at the lead coefficients, no work would be necessary. Now, that being said, on the free response, if they're going for you to use L'Hopital's rule, they're going to force you to use L'Hopital's rule. So if this was part of a free response question, it would be a small part and you probably wouldn't use L'Hopital's rule. So yes, none of that notation would matter. You could easily just do it in your head.
Thank you, Michael. Does that help? So this notation is to set you up so that if you want to do L'Hopital. If you show, because L'Hopital is kind of like a little trick, you're doing the derivative of just the top, the derivative of just the bottom. You're not doing like algebra techniques. So if you're using any algebra technique to fix it, you don't need that. You just need to show this if you're going to use L'Hopital. So let's look at one for L'Hopital because there are some on here. Let me find the ones that's got L'Hopital just so you can see, since we kind of confused you a little bit. Let's find a good one. Let's see. Let me look at what number 3. Let's look at number 3. That's a good one. So let's look at number 3. For sake of time, we're just going to jump right in. So we're doing the limit as x goes to 0. Now, if I look at this and the first thing I do is sub in and say, oh, that's 0 minus 0, 0 plus 0, that's going to be 0 over 0. If all I do on a free response is say 0 over 0 and then jump straight into L'Hopital, I lose my point. So I can't do this and then go straight into, and I'm going to skip over a little bit and jump straight into using L'Hopital to actually solve it. And we're going to use L'Hopital over here in just a second to solve it. So I can't do that. But what I can do is, so then I need to look at it and decide, am I going to do algebra to this? Can this be factored? Can I do a conjugate? Can I do any of those things? If that's what I'm going to do, I'm in good shape. But if this looks like something they want me to use L'Hopital, and like Michael said, this is the kind of thing they're going to give you to force you into using L'Hopital, because you can't do anything to this. There's no fixing this little snowman other than L'Hopital. Now, students love L'Hopital. And so what I see is most students are going to try L'Hopital first. They're not going to factor and do all those other things if L'Hopital works. And so if I'm going to use L'Hopital on a free response, a multiple choice, they don't look at your work, who cares? Do this and go straight into L'Hopital. But on a free response, I would have to say the limit as x goes to 0 of 7x minus sine x is 0. And the limit as x goes to 0 of x squared plus sine 3x is equal to 0. Now, it is my understanding that a student does not have to say, I'm using L'Hopital. At this point, if they start using L'Hopital, graders would understand that. The reader would say, okay, yeah, they're doing L'Hopital. You don't have to name it. Because sometimes
That's
they
correct.
want you. Okay, I'm glad you're on here, because where you've graded and read, you can help me out there.
Well, the misconception there is because when you do look at the scoring rubrics College Board puts out, it says by L'Hopital's rule. So then as a teacher, you think, oh, they're supposed to write that.
Right.
No, you don't have to write that. Yeah.
So this you don't have to say. Now, again, I know these are multiple choice questions, but I feel like it's important to talk about things for free response as we go. So now you would just go straight into your L'Hopital. So you would say the limit as x goes to 0, and now you can actually do your L'Hopital's rule. So the derivative of the top would be 7 minus cosine x over the derivative of the denominator, 2x plus 3 cosine 3x.
And another big mistake students make is they leave the limit as x approaches 0 off on that. They just write the derivatives, and that you will not get the point.
Okay, so let's make ourselves a note. Be sure to include. And I can't spell include. Students get lazy and they don't want to write that. And in their homeworks, it's really important in your homework, students, that you do this, because if you get lazy in your homework, whatever you do in your homework, you're going to repeat on the test. So if you're lazy in your homework, you're lazy on the test, and you will lose so many points because of that you don't want to lose. You want every point you can possibly get. So making sure you carry down that limit. You can't drop the limit until you actually do it. And doing the limit means you sub it in. So, and I tell my students, you can sub in anytime you want. But if you sub in too early, you're still going to get 0 over 0. So when in doubt, go ahead and sub in. And if at that point you still get 0 over 0, keep going. So if I sub 0 in to this one, it would be 7 minus the x value 0. So this would be 6 in the numerator. If I sub in 0 to this, it would be 3. So 6 over 3 gives me 2. Okay. For sake of time, let me look real quick at the other questions and pick out the best ones, just because I don't want to. We're going to run out of time. Oh, they're all so good. It's hard to leave any of them out. Okay, let's go ahead and look at, and like I said, I'll take this whole packet that I've given you and I'll work them all out. So even the ones we don't get to do together, I'll go back and work for you guys just so you can have an idea of what they all are. And actually, we've only got about 5 minutes. So I think, so if you look, I think I'm gonna have to move on just because we don't have a lot of time. And I think the rest, once you see them, you will be okay with them anyway. So if we go back to the front of our notes page and we look at what we've talked about so far. Okay, so what you need to know so far is how do you show and justify that you have a limit that exists on the test. So a limit exists if from the left and right they are equal, and you have to make sure you state that. And then if you do use L'Hopital, making sure you know to separate it out. Don't just put 0 over 0, infinity over infinity. Make sure you separate that out. And then not forgetting that you can still do all of this algebra as well. And like I said, I will do an answer key and I'll make sure you've got all those. My email is on there. So students, if you ever have a question about any of the stuff that's on the packets, please, 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 please. This was just so much to try to do in a day. It was just hard to narrow it down. Okay, just real quick, continuity. The only thing with continuity that we'll talk about real quick, if you know limits, you pretty much can do continuity. The only difference is for continuity, you have to make this last statement. So you have to have a limit, which means the left and the right are equal, which is what we said. And you also have to show that there is an actual value there. So if there was a hole, the hole got filled in. So the limit exists. So from the left and the right, so not only from the left, from the right, I came to the same place. So that limit exists. As I approach this number, whatever it is, from the left and the right, it does exist. But if the point is down here, it's not continuous because I have to lift my pencil. So I want to make sure if there is a point that it is actually the same as the limit. So you have to show that the limit exists, the value exists, and that they're equal. So basically the same things that we've been talking about. And we're going to do a couple of multiple choice here in just a second. That goes along with that. Another big deal that I wanted to make sure I say, this wasn't necessarily in this session, but I looked at all the topics and this is nowhere in any of the other topics, and it is so important, I feel like, is that just because a function is continuous does not guarantee differentiability. And they will ask questions about this. So what you need to know is this one. This is the one that we're going to look at today. You can show that it is not differentiable by showing it's not continuous. So if you look at something and it's not continuous at a point, it is also not differentiable. That's the only thing you can say. You can't say that because that's continuous, it's differentiable. There are things that make that not true. So things that make it not differentiable, I just added this on here just as a little blurb at the end. This is not in this packet, but just so you'd have it. You can't take the derivative at a vertical asymptote, holes, jumps, all those places where you're not continuous. Cusps and corners, so like an absolute value function at the corner. If you have a cusp, and I can't draw these as well, but something like that, that's real sharp, it will not be differentiable there. Or anywhere that you have a vertical tangent line, so like those functions that well, I can't get one, I can't think of it in my head how to draw it, but like your cube roots, the things that your vertical tangent line, your tangent line is vertical. So let's just look real quick at a couple of these and then we're going to take a break. So I apologize, I feel like I'm all over the place. Let's look at number 4. So number 4 is a perfect example of how they would ask something about, do you know what it means to be continuous and differentiable? This is how they would ask that. Now remember, not continuous means not differentiable. That's it. That's all we know. So at x equals 3, we have a piecewise function. So that means when you have less than 3, so as I come in from the left, what's my graph doing? So this is telling me from the left. So if I sub that in, it's coming into 9. This is greater than 3, so this is telling me I'm coming in from the right. So if I sub in 3, I would also get 6 times 3 is 18 minus 9, which is 9. Okay, now I want you to read those choices and see what you think. Oh, do you see what no, I did it right. I was going to say, did I do that right? Okay. So I know it's continuous. So if I were on a free response to show continuous, I would say that the limit as x approaches 3 of my function is equal to 9. And then I would say that f of 3 is equal to 9 because look at this. That says it's also equal to that value. So I know it's continuous. Okay, so it's not undefined. It's not that one. So now I have to decide, is it differentiable? This one says not continuous. So see how I go through and just mark out things? So now I have to decide, is it continuous and how does the differentiable part come? So you would have to look at this, and Michael, if you've got a better way to do this, please tell me. For this one, I would just look at it and say, well, I have a parabola. So at x equals 3, you've got a parabola and then you've got a line. And just knowing that that's what you have, you would be able to determine whether it's differentiable or not.
I would have to say, though, it depends on if those slopes match up.
Okay. Do you care to talk about this one then a
No,
little bit?
I would, yeah, no, I just take the derivative of the top and the bottom function. So 2x over 6, then plug in 3.
So you would have 2x.
And then the bottom would be 6.
And then when
and then at 3. Yep.
So since
so there's
equal,
there's a smooth transition of that 6 slope. Therefore, it is differentiable. There's not a cusp or a corner.
I'm so glad you're here. So you can do those little things. Okay, and there's another question on here that asks you to do this, and so you'll see that. So if you see that they're continuous, then you would want to show, because that's why your cusps and your corners don't work, because you don't have this smooth transition of your slopes. So if you can show that your slopes are also equal, then it would also be differentiable.
I've seen some that try to trick you, because some students are like, well, why don't I just skip to the second part? So they take the derivative and they match, and they're like, okay, we're good. But they didn't check for continuity at the start, and it turned out that they weren't connected there. Even though the slopes match up, they don't connect. So you do have to do both parts. Make sure it's continuous before you skip to taking the derivative and checking for differentiability.
Everybody okay with that? Just real quick, and then I said that was our last one, but I still have this last one. Look at 13, just so you can see, again, the kinds of things, the ways they would ask it. So if we just try to sub in, this is going to give me 0 over 0. If you factored it one way, just because we haven't done one, when you factor, the x minus 2's will cancel. So now when I sub in 2, I get 4. But the actual value, so if I'm thinking about the limit as x approaches 2, so anytime you see this notation not equals, that's kind of like saying what your limit is, because it's saying it's not, it's everywhere but at 2. So at both sides, somehow I'm coming into a height of 4. I don't care what it's doing, but it's coming into a height of 4. And then when I go to when it's actually equal to 2, I'm at a height of 1. So you have to understand when it gives you these piecewise, it's not always greater than and less than. So not equal to is kind of like your limit. Now you could have done L'Hopital on this and got it as well. I just wanted you to see one where you could have factored. So we could have L'Hopital this and got 2x over 1 and subbed in 2. So now, does it have a limit as x approaches 2? Yes, the limit does exist. It's 4. Is it continuous? No, because we have a hole. As soon as it's not continuous, it's not differentiable. So do you see the difference? I wanted you to see that. As soon as it is not continuous, it's automatically not differentiable. You don't have to do anything else. But if it's continuous, you still have to prove differentiability. Okay, I feel like that was a whirlwind of just a lot going on. And so, like I said, I'll make out all my stuff nicer and neater and post it so you guys can see that. If you've got questions about that, stay put. It is 11, so we're going to take about a 5-minute break and be back at 11:05. So go use the bathroom, do what you need to do, and we'll be back at 11:05.
Everyone at 11:05.
Okay, is everybody back? I have it being 5 minutes up, so hopefully we're back. Just real quick in the chat, let me know, student or teacher, whichever you are, have you covered integration by parts and partial fractions yet? Yes or no? And that way I know to approach this as the first time you've seen it or this is a review. So just real quick, yes or no, have you seen integration by parts and partial fractions? So one yes, one no so far. Anybody else want to admit where you are? I know a lot of people have not done this, especially if you're doing A, B, and BC all in the same year. Okay, so we're kind of split. Okay, so I'll try to say enough that for those of you who have not done these before, you will get to see enough that you understand what we're talking about, kind of a thing. So integration techniques, and this is going to be continued on into the next session. So you'll have 3 sessions on this. You'll have mine where we do both integration by parts and partial fractions. Then your next session will start with wherever we end on partial fractions and keep going with improper integrals. And then there's a whole nother session on when do I use each method, like how do I decide? So today we're not necessarily focusing on how do I know which method to use, but I still think it's important to include that as we go. So we will talk about that some, but you will get that more. So I just started on your notes, and I retyped these notes, and I guess I printed out the old version. So I've got handwriting on this one, so I apologize, but you all have the correct version. So don't forget to try your old methods first. So I always tell my kids, just because we learn some new fancy thing doesn't mean everything now is fancy. Just because we can do integration by parts, everything doesn't automatically become integration by parts. So these 2 methods, I call them my last resorts, which is probably a bad thing to say, but don't forget when you're doing integration, you still have all your normal things. So you still have normal undoing the power rule, which isn't proper wording, but just your normal take the antiderivative of something. Don't forget, you can still rewrite things using algebraic manipulation, like you can still bring things from the denominator to the numerator and multiply them in. You can still do all kinds of those things. You still have basic trig integrals. You can still complete the square to fix it. You still have long division. If you don't do any problems with long division, you probably want to do some just to make sure you're okay with that one. And then don't forget U-Substitution. So all those methods are still there. And I always tell my students, try all that first. But if you're looking at an integral and you're like, oh, none of that's working, then think about, oh, I have those 2 other ones that we didn't use real often, but when they're very helpful when I need them. And one is integration by parts and one is partial fraction decomposition. In general, if you have a product, so if you remember when you do derivatives, you can't just do the derivative of a product. You have to either fix it somehow that it's not a product, like distributed or FOIL or something like that. But if you can't, then you needed the product rule. Same thing is true for integration. We can't just do integration of a product. You either have to do a U-Substitution or something to fix it to do the integral. The same thing with natural log. If I asked you what the integral of a natural log is, it is not 1 over x, which is a common mistake. So when you have a natural log of x inside of your, that you're trying to take the integral of, what do? So products tend to go towards integration by parts. If it's rational and you can't fix it in any way, then try partial fractions. So some of you have never done this, some of you have. So this session is more about, let's just work some problems. I think last session was more about understanding what was going on. When we look at these, we're mainly going to look at how you actually work the process and what the AP exam will accept, more so than looking at a bunch of extra questions. So we're just going to work through some problems so that you can see how to do the methods. And then any question on a free response that asks you to do the integral could be this method. So we're going to look at it that way. First one we're going to look at is integration by parts. Now again, we said integration by parts is good when you have a product. So when you have something times something. And so when you have a product, and this doesn't necessarily look like a product, then, or you have a natural log of X, we're going to try integration by parts. So this first half of the day, we're going to spend on integration by parts. The biggest thing for students, and if you look this up, students, and you say, how do I pick the U part for integration by parts? How do I pick the DV part for integration by parts? You will find every teacher has a different way of doing that. There's all kinds of little acronyms and things to say, oh, S, that means this. T, that means this. So look that up. If what I tell you today is not helpful, look it up, and there'll be all kinds of other teachers saying how you pick things. This is what my toned down version is. When you're picking your U and your DV, what you hope happens is that whatever you pick for your U is easy to find the derivative of. It differentiates easy. You usually want it to get smaller. For example, if you're choosing between x squared and sine of x, if you choose x squared and you keep finding its derivative, it's getting smaller and eventually goes to 0. If you chose your U to be sine x, it just goes back and forth between sine and cosine. Sine goes to cosine, the negative sine, and as you go, it doesn't shrink down to something smaller. It doesn't always work out nice and neat that way. So sometimes that doesn't work, but usually that's what you want. And then if you have a natural log in the problem, it has to be the U part, because whatever we make our DV, we're going to take the integral of it. Your DV has to be something that you can integrate, so you can't put ln x over there. And you hope that it's pretty easy to do. You don't want something that's very complicated that you're trying to find the integral of. Things that are important to know for the AP exam. You may have to do the process more than one time to get it down to an integral that you know what to do with. So you just have to keep doing the process. So you do it once. If what's left inside of your integral still needs integration by parts, then you would do it again and again. We'll look at some examples. If that happens, this is a good time to use the table method. So if you look at it and it looks like something you're going to have to repeat the process over and over and over, a table sometimes makes that nice. So you are allowed, unless this has changed from back when I got trained years ago, you are allowed to use the table method, and we'll look at the difference in the formula versus the table method on the AP exam. Make sure your table's labeled well, like with any table. You can't just throw a table on the exam. It's got to have good labels on it. Make sure you don't just know one way or the other. You don't want to just, like my students want to just use the table all the time because it's easier to them. And I'm like, you can't do that though, because sometimes they're giving you everything as notation or in a table already that doesn't fit the table method. So make sure if we do this today and you say, ooh, I'm just going to do the table method, why am I doing that other all the time? You can't. You got to be able to do both. Because sometimes if you have to pick your U and it does not go to 0, then you don't know when your table ends. So one reason why you don't get to use the table method all the time is the only way to end your table is to have 0 times something in the other column. If this never goes to 0, it's hard to know. It's like, when do I stop? I could keep going forever. So that's one reason. If the question's asked and you can't put it in a table, that's another reason why you would want to use it the other way. So we're just going to jump into some questions and look at when to use it, when not, and when do we have to do lots and lots of extra things. All right.
And Miss Hill, you're right that the table is still allowed. It's just they're super tricky now and they write the problem that if they're trying to test integration by parts, it's probably not going to be useful to use a table. They're probably not even looking for the final answer. They'll just say, here's this, what would be the next step in the integration? And the multiple choice would be all the formulas. And you'd have to just know what the formula is supposed to look like. So you're right about that.
So make sure as a student, you recognize both. So if we look at the problems we're going to look at, if you look at number one is exactly like what Michael's talking about, like something like that. You can't just do the table method on that. So we're going to come back to that one in just a second. I want us to look at 2, 3, and 4 to start with. So look at 2, 3, and 4, and I want you to tell me which of those three could I still use U-substitution. They're all products. So we have a product, and a product. And so I'm going to have to use U-substitution or integration by parts. So I need to know which of those 2, 3, or 4 can I do U-substitution on. I see a number 3. Anybody else want to venture to guess? Okay, so only one person will tell me. So to do U-substitution, remember your composition, whatever you're taking the cosine of, the x cubed, if that becomes your u, when you find du, it has to give you something that matches what's out here. So if this is an x squared out here, when you take the derivative of your u, you have to get an x squared. I can fix the 3, but I can't fix the x squared. So this could be a u substitution because we have a u prime with a u. So this one would be a u substitution, and I'm not going to take time to do the u substitution. You should get B for that one. I'll put it on my answer key, but I don't want to take time for that. But these two, if you notice, they're not. If I try to use substitution on this one, u is 6x, du is 6. Well, there's no way that I can balance this out. I can't sub in u and du and recreate this in a manner that I know how to do. So when that happens, and again, those are the kinds of topics that I'm hoping they'll talk to you about whenever they do which method to choose at one of the later sessions. So we're going to focus on, okay, if I can't do U substitution, what does integration by parts look like? How do I do that? So we're going to do it first the good old-fashioned way. Let's just use the formula. So what I always make my students do is we do homework, and students, I would encourage you to do this. When you have a formula that you're going to use, write it down every time you use it. The more you write it down, the more likely you're going to have it memorized by the end of your homework. So if every time I use a formula, I write the formula down first, it's forcing me to memorize the formula. And so this is what your formula, the part of the formula that we're going to use, looks like. When you have integration by parts, and this is on the front of your paper, you end up, the formula is u times v minus the integral of v du. So this is what I'm going to come up with, and I didn't write the other side down just because I don't have room, but if you had it, it would be the integral of u dv. Okay, so there's my formula that it's going to force me into using. So if you practice it on some of these easier ones, when you get to questions that aren't easy, you're able to use it for them too. So I have to pick, so the first step is always to pick a u and to pick a dv. Okay, so for me, when I pick u and I pick dv, this is how I write it on my paper. And I learned this from, if you've never watched videos on corpysworld.com, this is how he wrote it, and my students liked it. So I thought, well, I'll just keep using it that way then. So my u is either going to be x or cosine x. So those are my things I'm choosing between. So if I look at that, I'm trying to find the one to pick for u that if I take its derivative, it's going to get smaller, hopefully. So I'm going to pick my u to be x, because when I take its derivative, it becomes 1. Now, that means cosine x has to be my dv. So in this method, for those of you who've never used it, whatever you pick your u, you find its derivative. Whatever you pick for dv, you're going to find its antiderivative or do the integral so that you can get v. So I'm going to take the integral. And I know the integral of cosine x is sine x. Okay. Now, the formula, if you have it memorized, says that you would do u times v first. So u times v would be x times sine x, and it comes out of the integral. So you've got a part of it that comes out, minus the integral, and I always call that voodoo so that I remember my brain VDU, voodoo. So minus the integral of voodoo, and we hope that voodoo is integral. That's something I can do the integral of. And then you would do V du. I think I actually worked this wrong on my paper that I've worked out last night, so it's not matching up. So does anybody see anything I've messed up on? The integral of cosine is really sine. X goes to 1. If you all catch me in a mistake, please tell me. So what I learned, what Corby's World says, he calls this the backwards Zorro method. So he writes it out like this, and he says it's like backwards Z. So it's like you're going this way and you make a backwards Z, and that fills in your formula for you, which works as long as you have this. If you're in a chart or something like that, it doesn't work. So you still need to have the formula memorized. So now what you hope happens is that this we can take the integral of, which we can. So x sine x minus the integral of sine x would be negative cosine x. So I'm just taking the antiderivative of sine x, which is negative cosine x, and don't forget your c. And then negative times negative is positive. So it would be b. And somehow when I worked it last night, I got C. So if anybody sees a mistake I made, please tell me. Okay, so just real quick for those of you who have never seen the table method, just so you can see it, is the integral of cosine. Okay, so we're good. If you want to use the table, you have to be careful. So here's how the table would look, and I'm only going to do the table this one time on this one, and then we're going to move on just for sake of time. You would have U and you would have dV, and I did put the table on your notes, so it's on the back of your notes, so you've got it. That's what it's talking about. Be careful with your signs. You have to remember that it alternates. So this little subtract in the middle, you have to take care of that in your table because it changes the signs of everything that comes behind it. So your first one would be plus, then minus, then plus, then minus, and you have to keep going in hopes that your u eventually becomes 0. So if we picked our u to be x and our dv to be cosine x, and then you would just do the same process. So I would take the derivative of x is 1. The derivative of 1 is 0, so I'm done. I would need to do the same amount over here. So the integral of cosine x is sine x. Sine x becomes negative cosine x. And now what we would have to do is go across. So you would have positive x times sine x. And notice it matches what we got here. Then you would have -1 times negative cosine plus cosine x. And then that one's just 0, and that's when you know to stop. So that's what a table would look like. And like I said, you can use that on the exam, but as Michael said, they're going to try to force you into not being able to. So you want to make sure you don't, as a student, only do everything by the table. I tell my students, if you're tempted to use the table, do both. It's a good way to check yourself on your homework, and that way you're learning it both ways. On the exam, you get to choose, but in your homework, do it both ways. Okay. Next. Let's look at number 5 real quick, and then we're going to look at some of the ones that force you into not using a table. Number 5 is one that gets my students all the time, so I just threw it on here just to make sure we remember. Anytime you have a natural log of x, you're probably going to use, or you are going to use integration by parts. And this does not look like a product. So we're like, well, it's not a product, so what am I going to pick my other piece to be? So we're just going to set this one up, and then you would be able to finish this one on your own. I want us to focus on the ones that look more like this. So we would say that our u has to be the natural log of x, because if I pick dv to be the natural log of x and I try to integrate it, I can't. So I can't pick it to be my dv. So then what do I use? So think about any product. Think about way back to Algebra 1 when we said, when we had parentheses and we were distributing and there's nothing out there, what's understood to be there? A 1. Same thing's here. It's understood to be a 1. So your dv would be 1. And so you would have 1 dx, or you could just put dx. That's fine too. And now you would do your u prime is 1 over x. Your v would be your x. And then you would fill in your formula. So if you're thinking backwards Zorro, however you want to think about it, the formula says u times v. So there's u times v minus the integral of v du. And then from there, it's easy because you can cancel those out. So you would have x natural log of x minus x plus c. Okay, let's go back to number 1. Go back to number 1. And this is where we'll end on this particular part. And then we'll move on to partial fractions. So integration by parts, as Michael says, they're going to give you something like this. So if all I knew was that table method, I don't really have a way to set up my table necessarily. So they're going to try to force you into, okay, recognize this is an integration by parts and do it using the actual formula. So I want you to just real quickly look at that. Okay, 2 things to clue you in that this is probably an integration by parts problem is that this is a product. If you looked up the formal definition for integration by parts, this is the notation they would use. So this is a lot of the notation in a lot of our textbooks and things. I didn't include it on mine just because I'm used to using this, but that would be a lot of textbook things. So if we have this integral and we're trying to show that or we know that it equals 5, and then it wants us to find this. So this is what I know. So I tell my students a lot of times, take what you know and figure out everything you can about what you know and see if that gets you to what you're trying to find. So if we look at this one and we know that this is true. So I'm going to write mine up here. So I know that from 0 to 1 of f prime of x, f prime of x times g of x dx equals 5. Okay, so the only thing I could do is take the integral of this. So I can do the integration. I know how to do that. So this is what I know, and I know how to find the integration. So go ahead right now and think about what you would pick. Since this is a product, can't do U-substitution, can't do anything else, so it's integration by parts. What would you pick U to be, and what would you pick your dV to be? Now, the good thing is, if you pick it and you start working the problem and you're not getting anywhere, go back and re-pick it the other way. Now, if you're thinking getting smaller, if I put f prime of x here, and I want to find its derivative, it's going to be the second derivative, then the third derivative, then the fourth derivative. So my notation is kind of growing, and I don't know anything about second and third derivatives. So that probably means I'm going to pick g of x to be here and f prime of x to be here. So go ahead and find your antiderivative and your derivative. So u prime would be g prime of x, and v, if I take the integral, is just f of x. So what do we have? We would have u times v, so g of x times f of x. I have both of those over here in my chart, so far so good, minus, and we're going to evaluate that from 0 to 1, minus the integral of v, so f of x, du. And I wrote it as u prime instead of du, but so g prime of x dx. Now that looks like it didn't help me a whole lot because it didn't really, this part didn't get any easier. But look at what I'm trying to find. So that's one thing they will do, is they will want you to find a piece of it, or what's the next step kind of thing. So I know this is equal to 5. So I can go ahead and work this out. So I know that if I am evaluating from 0 to 1, I'm going to sub in 1. So I would have g of 1 times f of 1 minus g of 0 times f of 0 minus the integral, and I should have put my bound 0 to 1, of 0 to 1 of f of x g prime of x dx equals 5, and this is what I'm trying to find. So I just need to figure out what these numbers are and get this by itself. So g of 1, I can find that in my chart. G of 1 is 3. F of 1 is 4. Minus g of 0 is negative 4. F of 0 is 2. So this becomes 20. 20 minus my integral. So I could subtract 20. So it's equal to negative 15. But since it's negative, when you divide off your negative, it becomes positive 15. Okay, so for those of you who are studying for your AP exam, when you get to integration by parts, the things you need to think about is, when do I use it? So if you have a product you can't do anything with, or you have a natural log, those are two ways. Yes, you can use the table, but make sure you know how to use the actual formula, because that's probably what they're going to require you to do in the questions. And then going back on AP Central or anywhere and finding these questions that look like tables and look like things other than what we're used to seeing, just on a normal textbook question is what I was trying to say. So that's integration by parts, only because it's 11:38 and I need to get moving. So hopefully for those of you who had never seen this before, it kind of gives you a heads up as what's coming. If you have seen it, hopefully you at least saw something new that maybe you had not seen before. Michael, do you have anything else you would want to add about integration by parts?
I do not. I think you covered it very well.
Okay, thank you. I did have this on there where it says find the value of f of 3. So this is how it could appear on a free response. So to find f of 3, you would be taking the integral of this. So it would be like your initial condition plus the integral of this, and that would be an integration by parts. And I'll have this worked out on Google Classroom for you. So this one would be f of 3 plus the integral of no, f of 1 from 1 to 3. And so in order to do this, you would have to know integration by parts. So that's what I said. What they do on the free response is no different than the multiple choice. It's just when you have to find an integral. Okay, and like I said, I'll have all these filled out. Same thing's going to be true when we talk about partial fractions. So when we talk about partial fractions, we want to, again, think about how is it going to be asked. And these are usually what I've seen them as is more or less multiple choice questions, but they could be more. Now, I did not find any good ones on this one, or I don't have good ones that's from like a chart or something else. So when we are looking at integrating using partial fractions, this is useful when you have a rational expression, you tried long division or it doesn't qualify for long division, U-substitution does not work. In the past, and I'm assuming it's going to continue to be this way, you can use the shortcut on the AP exam. And so what I want us to look at on your notes page, and I've put my notes page over here. Got too many pages in front of me. So basically what integration by parts is doing is saying, like, you have a rational expression, and I'm just going back to the basics. So for those of you who haven't seen this before, this is what we're doing. You have this rational expression that you can't do the integral of. So could we break it into little pieces and do the integral of each little piece? So we're allowed to break apart anything as long as we do it mathematically correct. And so if you think about this, if we're thinking about, well, how could I turn this into something, into two pieces? So it's like, what would I have to put on top here? What number would go here so that these are equal? And that's what you're going to be looking for today. We're looking for the number that when we factor our denominator and break it into pieces, what number can go on top that's going to make it all equal? So for example, if I'm thinking common denominators, 4 times something and 3 times something. And so this would be like 2 and 1. So if I had had 2/3 and 1/4 on there, when I found my common denominators, it was 11/12. So that's the basic idea behind what it is we're actually doing with partial fractions. So if you noticed on your notes pages, the last two was like an entire page of what's going on. So we are not going to do this method. I put it on there for those of you who just love pure math and you want to go back and look at that and think it's wonderful. So we are taking a rational expression, factoring the denominator, breaking it into two parts. The long way would be then find a common denominator and work it all out until you finally get down to the point where you found your A and B. So that would be the long way. Here's the shortcut. And so it's on there. Anyone in calculus, I think, would be able to go back and follow that and know what's going on. So let's just focus on what we're going to actually do on the AP exam. So we're just going to work through a couple of problems because I think that's the nuts and bolts of this part is just, can you do it? There's not a lot of extra like tricks. Well, they might ask it to you this way or that way. It's more or less just, here it is. Can you do it? So if you'll notice, they're rational. All the examples I gave are rational. Some are factored, some are not. And so sometimes it gives you the factors, sometimes it doesn't. So let's start with number 1. Let's just go ahead and start from the beginning. So this is already somewhat factored. So I look at that and I'm thinking, I don't know how to do its integral. I can't do any algebra to it at this point to fix it. There's nothing I can do. But I know that anything rational that I don't know what to do with, I can do integration by parts, breaking it apart. So I'm going to turn this into something, and luckily it was factored for me. That looks like this. Now we're going to use, and I'd never known what this was called, but I've been reading and it's called like the Heaviside method, where this mathematician whose last name was Heaviside came up with this. This works. Now here's the key. It only works for linear non-repeating factors, which is what the AP exam sticks to. So if you had a factor that was not linear, or if you had x minus 1 as a factor twice, this method does not work. But the AP exam sticks to linear factors that don't repeat, so that we can use this. So if you want to look up the whys behind it, you can look up Heaviside cover-up method, something like that, if you are curious as to all that good stuff. And they even give you the whys behind it. So what you will do is find the 0 of your denominator. Okay, now I'm going to take that number and I'm going to sub it in to this. But if you notice, if I sub it into this piece in the denominator, it makes the denominator 0. So this is where the cover up comes in. You cover up the one you're working in. I'm working with x minus 1. So I'm not going to use it. I'm only going to use what else is there. So there's understood to be a 1 on top. And then I'm going to sub a 1 in to that denominator. And there's the number that I would have found to be in the numerator to make that true. Let's try this one. If I find the 0, it's -2. So I'm going to cover up that factor and sub it in. So I would get -1/3. Now, if you notice, we have a 1/3 in common. So I'm going to bring my 1/3 out in front just so I don't have to deal with it. And that would leave 1 over x minus 1. That's easy to integrate. Minus 1, since that's negative, it becomes minus over x plus 2. Be very careful with your positives and negatives, because that's going to play a part in how the answer is written, because natural logs that are subtracted become division, multiplied become multiplication. So you have to be very careful watching your signs. Just curious, for those of you who have done this already or have taught it already, do you do the shortcut method? Have you seen shortcuts, or did you do it the long way? Just curious if you don't care to tell me. Crickets. Long way. Okay, so a little both. So long versus short, meaning this is a shortcut that I just showed you versus having to do this process. So this process is what you would have done in Algebra 1 and 2, probably Algebra 2. And it involves systems of equations. It involves a lot of algebra. You can do it that way. And that's what I did to my poor students at first. And then I went to a AP training, and they're like, oh, there's this wonderful shortcut you're allowed to use. And I thought, oh, no, the AP exam won't allow the shortcut. But I learned at that training that you can. So it's nice as a student to see it both ways so that you know what's happening. But this is much easier. So now, usually, these end up in natural log situations. And so for students, you need to be careful that you don't just put natural log every time. And we're going to look at one next that you have to pay attention to, that it is not u prime over u just automatically. So if this is if I'm thinking about logs, u prime over u, well, that is u prime over u. So I can just say that that is the natural log of x minus 1. Minus, again, is that u prime over u? Yeah. Plus c. Because if it's not, you have to balance that out. You have to figure out what do you need. So now if I look, always use your answer choices. Keep going over here looking to say, have I done enough? Can I move on? And then sometimes it gives you a clue as to what happens next. So I've got this 1/3 out in front. These two don't have a 1/3, so I'm just going to eliminate them off the bat. And as soon as I see a subtract on natural logs, I need to think division. Mark out the multiplication. And you wouldn't even have to finish writing it out to be able to match it up at this point, but see how close the answers are, so just be careful. So we would have 1/3, and then don't forget your log properties. Division becomes, or subtract becomes division. So x minus 1 over x plus 2 plus c. So that matches A. Okay, let's look at one that doesn't come out quite so nice and neat because of it's not necessarily always just u prime over u every time. So let's look at number 5. Look at number 5 because we're almost done. Look at number 5. And this is where we'll end. And like I said, anything extra that I have over this, I'll post and put better answer keys and stuff like that. It may not be today, but as soon as I get a chance next week, I'll add that in there. So let's separate it out. And for those of you who already knew the shortcut method, there's just not a lot extra that I can think of to add in other than the be carefuls. Make sure you're careful about these things. So for this one, when I find the 0, it's 3/2. So I'm going to sub that in. So 7 times 3/2 over 3/2 plus 2. So 21 over 2 is on top in the numerator. This becomes 7 over 2, which is nice. So it's just 3. So this is what I have so far. Now look at this one. Cover it up. 7 times -2. 2 times -2 minus 3. And I get 2. Now I want us to focus on this one for just a second. So if I bring that 3 out, this one's pretty easy. U prime over U. So if I took the derivative of this denominator, it would be 1. So that part's good to go. But this one, not so much. So I know I'm going to have a plus 2 ln x plus 2. So I can go ahead and eliminate some things. So now I have to decide and look how they do their choices. They're going to give you the choice, assuming you did not recognize that this is automatically not always going to work. If I do the derivative of 2x minus 3, if this is my u and this is supposed to be u prime, that's not true because u prime is 2. And so I'm not going to go into a lot of details about fixing that because every teacher kind of does that a little different. Some teachers balance it out. So do your U-Substitution, balance it out. Some people fix it. I've seen it lots of different ways. So you would have to remember that you have to multiply this by 2 to make it work, but you have to balance it out by dividing it away on the outside. So now you do have, so I'm going to do this over here so that I don't mess up my notation. So now I do have what I want. So I fixed it. So that one had to have a little fixing before I could do it. Which is why it becomes A. So just to wrap up on this one, just be careful when you're doing integration by parts. It's for a rational that you can't really do any other way. If you use the shortcut, be very careful with like your positives, your negatives. I wanted to show you why that worked, but because of time, I don't have time. But if you're interested in that, there's some cool little things that show like the notation and as to why this is mathematically correct, and that's good to see. And so it's mainly just, do you know how to do it? Michael, do you want to add anything as to what else they might need to know for this?
No, I know when I first started teaching BC, I thought this was going to be like so difficult. And then I taught it and my kids were like, this is not bad. And then the real thing was I had to get on them for leaving out notation because they realized they all kind of worked out the same and they would just do them real fast.
Yes. And that's where you make this kind of mistake.
Exactly. Yeah.
And so that's what the AP exam is going to do. They're not going to give you probably a real basic one that just works out pretty. They're going to want to see, are you really paying attention to what's happening? And they might give you one like number 3 that's not factored. I recognize that it's factored, but this one's not. So just be careful about that.
Can I see that one at the bottom again when you scroll back down?
Yeah.
Yeah, I'm sorry, you may have mentioned it. The only other thing is sometimes you have put a negative in front of that 2x minus 3. like 3 over negative 2x minus 3. Up at the top. Just a new problem.
Oh, gotcha. I was like, I don't understand why you're doing that.
No, I'm just saying, no. I'm just saying if the problem was
okay, I'm with you.
a net, yeah. 3 over yeah. So when you end up getting the natural log, the chain rule would cause a negative to pop out. Kids forget that all the time.
Okay.
That's what I'm trying to say.
Okay, I'll finish that problem and put it in there.
You know what I'm saying? They
Yeah.
leave that one out. Yeah.
So the biggest key to this one is just don't get lazy and hurry. Take your time, because if you drop a negative in the middle and you say that it's multiply like this one and you say it's multiply instead of divide, or you put a negative in because all of them have been negative up to this point, but then this one pops up and that takes away maybe one of the anyway. So you just got to be very careful. That's my best advice for this.
Agreed.
So we've got 2 minutes. So Michael, I know you said you were going to like wrap us up at the end with some stuff.
Awesome. Well, thank you, Ms. Hill. This was very, very, very useful, and I found a lot of value in it. I hope everyone else did too. I'm going to share my screen here. Can everyone see? Can you see that? I know you can't now because I just messed it up. Try again. All right, now can we see that?
Yes.
All right. So again, thanks for joining us. Thank you, Ms. Hill. I liked your Heaviside method is actually even shorter than the way I do it, and I like yours. So I learned something new. You can reach Advanced Kentucky again at any of these if you need me or Aaron, who is actually the content director for the mathematics with the college readiness program. Those are our emails. Ms. Hill, it's okay if people email you, I assume?
Yes.
Okay. The handouts and recordings are here, and you said you would also get us a solution key.
Yes.
And next time is February 6th. We encourage you to come. The BC integration techniques part 2 will continue, and that's with Miss Hines, and Miss Hines was on here, so she saw where Miss Hill left off, so she knows where to pick up. So it would be a smooth transition, and then part 2, and then Euler's method and logistic growth with Miss Stephanie Hines. So we encourage everyone to attend that. Unless there's nothing else, there's some comments I'm going to go read here. But if anyone else has anything, feel free to email us. Thank you again, Ms. Hill, and I'm going to stop the recording. Everyone have a great day.
And if there's anything in the future that you guys have a question about, feel free to email me, because I know as a first-year teacher, so like Emily is a first-year teacher, I've reached out to some of my Advanced Kentucky people constantly with questions, and I didn't want to ask. I'd say, oh, I don't want to ask this because they're going to think I'm so dumb, but I had to because I didn't know. And just remember, reach out to any of us, because we started as a first-year teacher, and I'm still learning. Like, I'm going to come to all these sessions because I know that I will keep learning from all these people. So keep coming as a teacher, even if your kids don't, and reach out to those of us. I may not know the answer, but I know people who do. So please reach out if there's any questions about any of the content you're covering.
Thank you. Oh, did she leave? Oh, I was going to answer a question. Nope, she left. Well, I couldn't answer it then, sorry.
I didn't realize